Okay, welcome to the lecture 60 of this course Classical Mechanics 1, and this is the last lecture. And in this lecture we will cover the vibration of linear carbon dioxide molecule. So, before that let me recap what we were doing in last few lectures. So, this is lecture 60 in classical mechanics. One, and last few lectures we are discussing small oscillation. Okay. So, we know how to calculate, we have learned how to calculate normal modes and normal frequency. That we have seen, and we have discussed detail with a coupled oscillator problem, and also we have seen how to normalize these normal eigenfunctions. Today we will apply those concepts to discuss the vibration of linear triatomic molecules. Okay. So, vibration of linear and triatomic molecule, and we will consider carbon dioxide molecule, and this carbon dioxide molecule will model it as a mass spring system Okay. So, let me draw the system taking carbon atom at the center, and it is connected to two oxygen atoms both side, and we will consider that they are with the same spring constant K. Okay. So, this, and let us consider the mass of carbon is, so mass of carbon is capital M and mass of oxygen will be small m. Okay. So, this is a well known mass spring system, and we are considering the vibration in a linear one dimensional motion for simplicity. Real carbon dioxide molecule is not linear as we are considering here. So, this is one dimension. So, let us consider this dimension is as x direction, and at any time the position of the this first atom, that oxygen atom, is x 1, and then position of carbon atom is x 2, and this is x 3. So, it is a 3 degrees of freedom, and with this we can write the Lagrangian. So, kinetic energy T for the system we can write half m for the oxygen molecules oxygen atom x 1 dot square plus x 3 dot square, and the for carbon atom it will be capital M. So, m x 2 dot square. Okay. And then potential energy we should write. So, to write potential energy let us consider that x 1 0, x 2 0 and x 3 0 are the equilibrium position of the respective atoms. Okay. So, potential energy due to spring, it will be that there are two springs. So, there will be two potential energy. So, let us have a look that this potential energy will be half k x 2 minus x 1 whole square. This will be half x 3 minus x 2 whole square. Okay. And we define the variables eta I is just x I minus x I 0. That means, the difference between its any time position with the equilibrium position, that shift from the equilibrium. So, then you can write with this definition of eta, potential energy will be half k eta 2 minus eta 1 whole square plus eta 3 minus eta 2 whole square. Okay. And with this definition, kinetic energy will be reduced, because eta I dot is same as x I dot. Okay. So, we can write kinetic energy in terms of eta is half m eta 1 dot square plus eta 3 dot square plus half capital M eta 2 dot square. Okay. So, Lagrangian immediately we can find is, okay, we do not need to write the Lagrangian, but we need the V matrix and the T matrix. So, T matrix is very straightforward, T matrix is diagonal. So, it is M, capital M for eta 2 and small m. So, this is our T matrix, and for V matrix let us expand the squares. So, if we expand this V, it will be half k eta 1 square plus 2 eta 2 square, okay, plus eta 3 square, and you have 2 eta 2 eta 1 minus 2 eta 3 eta 2. So, this will be the potential energy explicitly. Okay. So, V matrix we can write from your knowledge in the last class is that, so eta 1 square it is k, and then eta 1 eta 2 it is 2, but it has to be symmetric. So, it will be minus k in that sense. Okay. And 2 you cannot take, because you have to be symmetric. So, you can write 2 eta 1 as a eta 2 eta 1 plus eta 1 eta 2. Okay. So, and then there is no eta 1 eta 3 term. So, it will be 0, and then you have minus k symmetric terms, then 2 k, because 2 eta 2 square, and then again 2 3 term is minus, and then this will be 0 minus k and k. Okay. So, then we can write this condition to find the normal frequency, that you remember V minus omega t determinant equal to 0. Okay. So, let us write that V minus omega t, V is for first term. So, in the determinant, first term is k minus omega square m, because 1 term is m in the kinetic energy, then this will be minus k 0, and this is minus k 0. So, only the diagonal term will change to k minus omega square capital M, and then third position will be minus k, this will be 0 minus k and k minus omega square M, and this determinant equal to 0. Okay. So, if we need to break this determinant and solve for the frequencies. So, let us do that. Okay. So, if we break it, k minus omega square M times the determinant to k minus omega square capital M minus k k minus omega square M, then minus k. So, and there will be a minus term from the determinant rule. So, minus k 0 and k minus omega square M. So, this will be 0. Okay. So, now next if we break k minus omega square M, and then within this bracket 2 k minus omega square capital M times k minus omega square M minus k square, and then plus k into minus k into k minus omega square M. Okay. So, this is the full term, and that equal to 0. Okay. So, now if you take this okay, if we simplify by taking this is common to all terms. So, k minus omega square M, and this if we write 2 k square minus omega square 2 k M 2 k M omega square minus omega square M k plus omega to the power 4 small m capital M, and that is with plus sign, then minus k square, and if I take this common, then it will be minus k square equal to 0. So, this term will get cancelled. I have 2 minus 2 k square and plus 2 k square. So, if we cancel that term, okay. So, if we cancel this term, so we will have k minus omega square M, and then omega will be common from all these terms. So, omega square, and then you have omega square M minus 2 k M and M k. Okay. So, this equal to 0, and now you can solve this and find the frequencies are omega equal to 0, because omega square is multiplied, and then omega equal to root k by M, and from this term you will get omega equal to root over 2 k by M plus k by M, which you also can write as root over k by M common 1 plus 2 M by k. So, these are the normal frequencies. So, what are the normal frequencies in this case? In this case normal frequencies is this omega equal to 0, omega equal to root k by m and omega equal to. So, let us denote this as 3. So, omega 1 is 0, omega 2 is root k by m and omega 3 equal to root k by m plus 1 plus 2 m by k. Okay. So, these are the 3 normal frequencies. So, now we have to find the normal coordinates, right. So, if we find the normal coordinates of this, so what we will do for this, let us consider the for omega 1. Omega 1, let us in following the last lecture's notation, this denoted as the vector as 1 1 and then 2 1 and 3 1, right. So, this is our notation for omega equal to omega L, the vectors was A I L. Okay. So, this was the notation. So, L equal to 1 in this case because omega 1. So, this is our vectors. So, we can write that this matrix k minus, and now omega equal to 0. So, it will be k minus k and 0 and minus k, then 2 k and then minus k 0 minus k k, and this a okay. So, let us write a 1 1, a 2 1, a 3 1 equal to 0, and from here you will find that a 1 1 minus a 2 1 equal to 0, first relation. Second relation will be minus a 1 1 plus 2 a 2 1 minus a 3 1 will be 0, and then minus a 2 1 and plus a 3 1 equal to 0. So, if you solve this equation, you will find a 1 1 equal to a 2 1 equal to a 3 1. So, all are equal. So, we can find, let us say our eta 1 first eigenvector corresponding to 0 will be 1 1 1 and multiplied by a 1 1, which we have to determine in a 1 1 has to determine from the normalization condition. Okay. So, from normalization condition, and how we will do this normalization condition? Normalization, if you remember in last lecture, that sum over j k t j k let me write this term again for you, t j k a k l and a j m was delta L m. So, I will show you one eigenvector how to normalize it, and then rest you can do yourself. So, this was the normalization condition. So, let us consider L equal to 1 and m equal to 1 case. So, you will have sum over j m t j k a k 1 a j 1 equal to 1. So, if I choose this equation, then this this will be the result. Okay. So, now we have already seen that a 1 1 equal to a 2 1 equal to a 3 1 for this frequency. Okay. So, now we consider this summation, we will break this summation. Remember, my T matrix is diagonal. So, only T 1 term will survive. So, T on j and k is 1. So, it will be 1 1 and 1 1 plus T 2 2 will be A 2 1 and A 2 1 and T 3 3 will be A 3 1 and A 3 1 and this is equal to 1. And now, if these all are equal, then I can take A 1 1 common and then you will have T 1 1 is m, T 2 2 is capital M and T 3 3 is small m. So, this equal to 1. So, giving A 1 1 is 1 over square root 2 m plus m. So, the eigenvector corresponding to the eigenfrequency omega equal to 0, we obtain that eta 1 is 1 over root 2 m plus k 1 1 1, all are equal amplitude. The other two result I will just supply, that for omega 2 that is root k by m, this frequency, we find the eigenvectors 1 2 a 1 2 a 2 2 a 3 2, right, in following our same notation. And this eigenvector you can find from this exactly same procedure what we followed, is that eta 2 will be 1 over root 2 m 1 0 minus 1. Okay. So, this is our second eigenmode, and now we will consider the third one. Okay. So, third one we will have omega 3 will be root k by m and 1 plus 2 m by m, this is the frequency. And what will be the normalized eigenvector? Following the same procedure, you will find the normalized eigenvector, the eigenvector coefficient will be 1 3, 2 3 and a 3 3. Okay. So, this will be the eigenvector coefficient, and if you calculate following the same rule, the T j k a k l and a j m sum over j k equal to 1, you will find that, and also the relation between a 1 1, a 2 3, a 3 3 you have to find. So, then if you substitute and use this equation, normalization equation, you will find, this I leave as exercise for you because we do not have time. So, it will be 2 m 1 plus 2 small m by capital M and a 2 3 will be minus 2 m by m root over 2 m 1 plus 2 m by m, and a 3 3 will be 1 by root 2 m 1 plus 2 m by m, okay, same as the first one, same as a 1 3. Okay. So, these are the coefficients. Okay. And now what is the physical interpretation of this? So, we had the system carbon dioxide molecule has model with a mass spring system. This is oxygen connected to the carbon. So, this is carbon, this is oxygen, and then it is connected to oxygen. So, apparently omega equal to 0 is little bit surprising and alarming also. This is actually no oscillatory motion. So, this implies no oscillatory motion. So, basically this will be a translational motion, that all three molecule atoms, C, oxygen and carbon, oxygen and oxygen, they are moving in one direction with equal amplitude. Okay. That also we have seen that A11 and A21 and A31 all are equal in this eigenvector. So, omega equal to 0 correspond to that translational motion, that all the atoms shift with equal amplitude in same direction. Okay. Now we will also see the physical meaning of the other two frequency. So, omega 2 that equal to root k by m. So, it will have the eigenvector, remember eigenvector, the middle one is 0. So, we can think of that you have this side the oxygen and this side is carbon. So, this has in this direction motion, this has this direction motion, and this is remain unchanged. So, it has no amplitude. Okay. And similarly if you analyze the omega 3, which is root k by m plus 1 plus what was this m by 2m by m, this frequency, then we will find, okay, then we find that this moves in this direction with a bigger amplitude, and this moves with a smaller amplitude, this moves in this. So, this is schematically the situation for a vibration of a linear carbon dioxide molecule. This same technique you can apply for many other molecules, particularly triatomic molecules and okay. So, this concludes this lecture. So, let me summarize what we have done in the small oscillation chapter. So, small oscillation we have learned that any potential which has a minima can have a oscillatory motion around the minima. So, that we have seen for one dimensional case, and then we have considered a general case to find the to find the normal modes and normal coordinates. Okay. And then we have so we know how in detail how to find normal coordinates and normal modes of a system. Then as an application we discuss that vibration in a carbon dioxide molecule by assuming that it is a linear and the molecule is replaced or modeled by a mass spring system, and we find the normal frequency and we have the longitudinal modes of vibration is analyzed. So, this concludes the course in classical mechanics 1. I hope you have learned to some extent the classical mechanics. At least I try to emphasize that you should able to solve many problems in classical mechanics. So, you will time to time you will get the home assignment sheets, try to solve these problems, raise your concern in the discussion forum, and we will meet live every month that we are meeting. So, with this I conclude this lecture. So, I hope you will have learned the classical mechanics to some extent. Okay. Thank you.